thank the organizing committee for, basically inviting me and placing me in the best possible time, like being the second one to talk. I'm currently now, I already have a job here at UAM Iztapalapa, so I'm happy to add the logo. I'm going to talk about this work that I did with Alan Dow 1 year ago, I think. So some of you might have already heard these before, but I think that this is an improved version of the talk. Okay, so first, this definition is, we're going to look at discretely generated spaces. And we're going to say that a space is discretely generated at a point if every time you have a set A whose closure contains that point, then there's a discrete set whose closure also contains that point P. So this is a very natural generalization of the Frechet-Urison property, for example. And discretely generated means discretely generated at every point. So this notion was defined in 2002 in a paper by these 4 people. And as I was saying, it's a generalization of Frechet-Urison, but we can have arbitrary large tightness. For example, we take a discrete set of size kappa, another point, another point, and whose neighborhoods are of a set with complement of size less than kappa and plus a point. So that's like a one-point compactification, like the Lindelöfification of a discrete set. And it's discretely generated clearly and has arbitrarily large tightness, well, according to the cardinality of kappa, or kappa. Okay, so I'm going to start by giving some examples, so we know what's discretely generated and what is not. Like there are large classes of nice spaces that are discretely generated. So if you take monotonically normal spaces and you take some products, countable products and box products, and I think that also sigma products, but I didn't write it here, you're still discretely generated. And an example of this is, well, a simple example of this class is a linearly ordered space. And if you want a space that is not discretely generated, you can take a maximal countable regular space. Maximal, I mean by the topology is maximal among all crowded topologies. And I'm not going to go deep into this, but the reason is that if you take a maximal space, any discrete subspace of it is closed. So it has no accumulation points or cluster points or whatever. Okay. So now, next. So the topic of the title of my talk was ad infinity, so I'm going to talk about compactifications. So let's start thinking about compact spaces. So it happens that compact spaces are weakly discretely generated. Every compact space has this property. That's like the sequential version of discretely generated. That means that a space set is closed if and only if the closure of every discrete set is contained in that set, or if you want to read it like this. That's not very important, but that's the reason. The proof appears in a previous paper by Kachuk. Okay, so that's a property that all compact spaces have, but what about discretely generated? Well, there's if we think about remote points, we're going to obtain spaces that are compact and not discretely generated at every point. So if you look at P at a remote point, then obviously there's no discrete subspace of R that contains P in its closure. And if in case I think Alan talked about this. No, not really. he said omega far, but it's similar. P is a remote point if it's not in the closure of any nowhere dense set. So in particular, if it cannot be in the closure of any discrete set. Well, of course, if we're thinking about crowded spaces. So this is the main question that I looked at when I was talking to Richard Wilson, like 2013. He was working on this. So if you have so what's the motivation behind this? If beta R has lots of points that are remote. This is a result of Van Douwen, a classical result of Van Douwen. So the set of remote points is even G delta dense. So what these three people, Alice, Unikata, and Wilson wanted is, okay, so we want a compact space that is discretely generated everywhere except possibly 1 point. So we can also think about this, like take a locally compact space that is discretely generated and take the 1 point compactification. Is it still discretely generated? And this is also what I mean by discretely generated at infinity. So it's just like take a locally compact space and add the point infinity and wonder if it's discretely generated or not. So before I arrived to this problem, or to this, to the problem, there were two results. One by these people under CH, and one by Aurici using a Suslin tree or Suslin line. So these examples are locally compact spaces that are discretely generated, but are even first countable. And their 1 point compactification is not discretely generated. So they are not discretely generated at the infinity. So that's what was known by that moment. So the first thing I thought is, well, let's try to do it under Martin's axiom, modify the first part of this theorem under Martin's axiom. So that's the first thing I can tell you about. This is essentially the cardinality consideration we need. We need cardinality of meager because basically you need cardinality of meager many nowhere dense sets in order to define a remote point with Van Douwen's technique. And well, I want to give you the proof of this. So, well, this first sentence is what you really need to prove using Martin's axiom for sigma-centered posets. You can construct a closed set that is remote from this space. So I'm gonna. Is there chalk? I didn't ask. Yeah. Thank you. So it's just. I hope this is. You take like omega copies of the Cantor set. So this is omega times the Cantor set, and you take the 1 point the Stone-Check compactification. Sorry. So this is the remainder, and you can find a set F that is remote. That means, well, I spoke about remote points, but remote sets are just the same. It's a set that if you take any nowhere dense set of omega times 2 to the omega, then the closure of this set will not intersect F. And I'm saying closed set. I don't need a point, and this sometimes. In order to get a point, you need more than cofinality of meager Klopen sets. So that's why I'm saying closed set only. And what do? And this set needs to have this special property. And it has a base that is linearly ordered in type P. So what you do now, you consider the quotient space. So each one of these rings or whatever you call them, you collapse them to a point. So what you basically obtain is a linearly ordered set. And you collapse F to a point too. So I'm gonna draw it again here. So instead of having this remainder, you're just gonna have 0, and you're gonna have P here. And I claim that's well, that's going to work. So why is it going to work? Well, first, this space, this quotient space, is discretely generated at the Cantor set times omega because of first countability, basically. Okay, so if you look at a point here below P, there are two ways that you can obtain a well, that you can think of a subset. If you have, let's say, X, I can write it here. If you have something like some set A such that X is in the closure of A, there are basically two cases. A could be like inside the Cantor set or down here below the ordinal X. And below X, no, what am I writing here? Local character is less than P. No, like if you look at the first cases, if A is like inside here, the character of X in this space is less than P. So filters with character less than P are Fréchet. So basically you can obtain a converging sequence to X, a sequence converging to X, sorry. And the other case is if A is down here. Well, basically this is the case when you're looking at a linearly ordered space, and I already said that using this monotonically normal theorem, there would be a discrete set, right? Then it's discretely generated at that point. Okay, so what's missing? The top point, or set F, that was collapsed to a point. Well, we chose it as a remote point, so basically that's why the space is not discretely generated at F. There's no discrete subset of the Cantor set cross omega that has that in its closure. So that was this example. So this is an example that you have something that is discretely generated, and then you add the point at infinity, and then it's not discretely generated. Okay? So after this, so that was before I visited Alan Dow. So then I started working with Alan, and I told him about this problem, and he said that surely we could solve this with PFA. So the idea is, well, not the whole problem. We're just focusing on locally compact spaces of countable tightness. So if you have one of these these spaces and it's discretely generated, then if you add 1 point, the 1 point compactification, then the space is going to be discretely generated at that point. So notice that this example that I told you about still exists in PFA. It's just that under PFA is equals omega 2, so this example in the blackboard is, well, doesn't have countable tightness, right? It has a copy of omega 2, right? Okay. So I'm going to try to give you like the proof or sketch of the proof. So you see the forcing argument. So start by fixing one of these spaces, discretely generated and countably tight and locally compact. And consider a subset A that is non-compact. So why? Because this is going to be the set where we have to find the discrete subset. And I'm going to call the point at infinity, infinity, by suggestion of Michael, I think. OK, so whatever you have outside A doesn't really matter. So we're just going to assume that A is dense. That means take the closure and then remove everything else that you don't need. And by doing some other, by taking some parts of the space out, we have two cases. The first case is when A is countable. And the other case is when there is no countable subset that has the infinity point at in its closure. And moreover, the infinity, that point has character omega 1 in the one-point compactification. So, by the way, case 1, I'm not saying anything about the character of point infinity, so it's only this consideration is only for case 2. And what's my next? OK, so the next slide is, let's start with the countable case. In this case, we don't really need PFA. So first, you have to, well, this should be A1, A2, but I didn't find, I didn't have the time to find how to write different indices here with metapost. So, well, basically, it's take A, then you can basically partition A into Clopen sets. So this is the picture of space X. So each of these is a Clopen set, or even a closed set. Well, it doesn't have to be zero-dimensional, but I drew the picture like zero-dimensional. So it's each one is compact and has dense interior. So each one is a regular closed set. And then you have what remains is y and the point at infinity. And this is the definition of y. So y can be okay. So before I say that, this picture is the same picture I drew in the blackboard. So basically, in this case, we have what we have in the chalkboard. Okay. So of course, if y is empty or y is finite, then there's going to be a sequence of points of A converging to infinity. So that case is trivial. So let's assume that we don't have that trivial case. So now we're going to divide again in cases. So the first, not so trivial case, but still easy, is if there is a countable discrete subset in Y that converges to infinity. Well, in this case, okay, so look at each point of D. So it's going to be a point here. There's going to be a discrete by countable tightness and discretely generatedness. There's going to be a point, a sequence of points here that has this point in its closure. So by an inductive argument, you can construct a countable discrete set, a discrete subset of A with all these with all D in its closure. So it's also going to have infinity in its closure. So that case is easy. Okay, so that was the easy case. So what if we don't have such a space D? Well, we need to use, we're going to use free omega 1 sequences. So it's a sequence indexed by omega 1 that has this property where whenever you split the sequence and you take closures, then closures do not intersect. And for this specific situation that we are in, that means that we're in a compact space, and everywhere there's countable tightness except at P, and P is not isolated, and this that is in bold font is not in the closure of any countable discrete set. That is exactly the case that we're in. Then there is an omega 1 sequence, a free omega 1 sequence, where P is the only complete accumulation point. So let's use this this free omega 1 sequence that we have in the remaining case. So basically, we're going to do a Cohen type of argument. So find an enumeration of each an and find the sequence that converges. Maybe I shouldn't. Yeah, it's not converges. Yeah, find a sequence like this that has XA in its closure, and then by Martin's axiom for countable posets, there's a function that is equal to each FA alpha infinitely often. Anyway, so using that sequence, you can find, again, it's not converges. Sorry. I was planning to write for a simpler argument, we're going to assume that X is first countable. So that's why it says converges here. But that was till the next slide. So here I'm going to assume that in order to simplify the proof. I only have 10 more minutes, and this is the hard part. This is the part that uses PFA. So before we start with this case, we have to remember a result by Shapirovsky or Todorchevich that says that if you have the result of theirs says that if we have a compact space with countable tightness, then there is a point countable pi base of X of that space. So here we don't have countable tightness, but we have countable tightness everywhere, but at a point that has character omega 1. So basically, there's still a point countable pi base of the space. Now I'm going to describe this forcing. So we're going to use this. We're going to use models as side conditions. Okay, so let me define the forcing. So the first part, or the first coordinate of a condition is going to be a finite set of pairs. So the first element of that pair is going to be a point in A. That means in the discrete set that we want. And the second coordinate is going to be an element of this point countable pi base. And the point has to be in that element of the point countable pi base. If you take two different pairs of these pairs in HP, then so it's a point and it's open set, and another point and it's open set. So this point cannot be in this open set, and this point cannot be in this open set. So that's we want that so that we can build a discrete subset. Now the third one is the second coordinate of this thing is a finite chain of finite epsilon chain of countable elementary submodels. You know that, I hope. And number 4 just says that the models separate these pairs of points and open sets. And this is a technical condition that we needed for to prove properness. We had to add it. Well, I'm not going to read it. I'm short on time, and extension just means extend. That means add more pairs of points and open sets and another model or something. And we don't have time to prove that it's proper, but I would like you to see why we want how this poset works after we know it's proper. So assume that there's a generic filter. Okay, so if you have the points that are in the first coordinate, yeah, so there's this is a mistake, right? There should be something like A comma B is equal to HP. Yeah. So yeah, so there's a P in the generic filter such that HP has a pair whose first coordinate is A. That's what I meant. So just take the points given by the generic filter. So as I was saying, this second property that was on the previous slide tells you that the set that you obtain is discrete. And if you take a base at infinity of size omega 1, then you can find these dense sets, these sets that are conditions such that there is one element of HP such that the point is in U alpha in the element of the base. So this is dense, and there are what am I going to do here? Prove that it's dense. So I don't know if I can. Maybe there's not enough time for this, so I'm just going to say that. Well, maybe go back to the previous slide to just say that this is dense. So basically, we have that the discrete set D is going to intersect every element of the base. So it will have infinity in its closure. So that's what we want. And I'm sorry, I couldn't give you the anything else. Okay. Thank you.
Any questions or comments? All right, so let's thank Rodrigo again.
Thank you.
And yeah, I guess I should remind you that